Good afternoon, everyone. Apologies I couldn't be there with you in person, but a warm thank you for attending my talk nevertheless, and an even warmer thank you to the organisers of the workshop for kindly inviting me to speak today. So in the brief time I have with you, I just want to cover off on a few key topics that I hope are relevant to the workshop and will help drive the conversation along with the other speakers and presenters as well. I'll briefly introduce myself and the research centre that I currently lead, the QT Centre for Robotics, including touching on a couple of projects that I think are relevant to what this workshop is about. Then I want to spend most of my time talking about three key aspects of how we conduct and, more importantly, perhaps evaluate and assess research. And I'm going to illustrate these in the context of actual industry or applied projects we've done, especially in the areas of autonomous vehicles, including as per my original title, in the area of positioning for autonomous mining vehicles. And once again, I hope that these drive discussion. I don't have all the answers, of course, but this is what's so great about workshops. We can provoke thinking and think about how we can continue to refine and improve how the field goes about research in robotics. So briefly, to introduce the QT Centre for Robotics, we're a large robotics research centre, over 100 people, including 16 or 17 academics, a number of postdocs, a large cohort of graduate students, lots of PhD students, engineers, professional staff, and so on. We do the whole range of research, from research for robotics in the skies to on the oceans, deep under the oceans, on the ground, off-road and on-road, and deep underground, all the way from fundamental blue sky research to highly applied commercial research that is actually deployed in enduring applications in the real world. Some of the applications, we spend a lot of time working in off-road or extreme environments. So we've had teams spend 3 seasons on the ice in Antarctica as part of securing Antarctica's environmental future, which is a large decade-long national research initiative in Antarctica. And you learn a lot from operating drones and then submersible robots in such an extreme environment. The workshop today is around collaboration and perception for, I guess, off-road environments and autonomous vehicles. One of the other ways you can partially solve this problem is in how you manage your fleets of vehicles, especially when you're deploying large numbers. And Professor Aaron McFadden from our centre has led a consortium of collaborators that has developed some of the unmanned traffic management systems that are currently in use at Australian airports that help keep drones and similar craft away from passenger aircraft. And these are all pieces of the puzzle in terms of designing complex robot systems that will endure around us in the real world. One of the big opportunities that is new to this field are obviously so-called large language models, vision language models, and foundation models. They really give robots 2 key new capabilities at a scale that we've never had before, which is the ability to act as if they have a common sense understanding and perception of the environment, and in the interests of collaboration and working around people, the ability to have a relatively sophisticated and intuitive communication interaction with the people that the robots are helping or are working with. And so a task like this, which is place something healthy on Peter's desk, so this is from colleagues at the QT Centre for Robotics. They have a number of really fantastic papers in conferences like the Conference on Robot Learning over the last few years. This is now something that is achievable, which was not anywhere near as easy to do just a few years ago, and would have inevitably been a more highly scripted demonstration. So there's a lot of exciting potential, and I think we're just starting to tap the surface or break the surface on what we can do in these areas. My particular area of expertise is in positioning, and most of the concepts that I'm going to illustrate today are in the area of positioning and SLAM and localization for autonomous vehicles and robot systems. I think it's a great area in which to illustrate some of these key concepts and explore them and think about them. But we also work in a number of flagship projects. We are one of a large consortium of Australian companies and universities and government that is working on building and deploying the first Australian-made rover to go to the moon, which is an incredibly exciting project. We are in the early stages of that, and once again, our team is responsible for the scene understanding and localization aspects of part of what the rover will do. We've also worked a lot in things like terrain traversability, terrain analysis. This was a project with an industry partner on doing advanced terrain detection for an autonomous ground vehicle and non-autonomous ground vehicles. This is a very edifying project in that we made a lot of progress, but also really got into the weeds of how incredibly difficult this problem is to solve at a level that's sufficiently reliable to deploy. And very different problems, I think, in many respects to the current focus on on-road autonomous vehicles. And if you want to read some of the general insights from that, we have a relatively recent survey paper in the journal Field Robotics on terrain traversability analysis. So methods, what sort of sensors you can use, and some of the open challenges. And this is by no means a solved field. So lots of interesting research to still do in this area. My particular group has spent much of the last 2 decades working on positioning for autonomy. So really scaling up in both time and space. So scaling up in time is creating systems that can do navigation at sort of millimeter level precisions in areas like surgical robotics, but also scaling up to, we have an initiative called the Local Positioning System where we're trying to create a global alternative to GNSS and GPS and all of the satellite-based systems. And scaling up in time as well, so systems that can work at sort of millisecond or even microsecond latencies, but also systems that can work on autonomous vehicles over long periods of time and robots. And so this sort of encapsulates what we do in this graph. We work in lots of fundamental research areas, but we do lots of work in the commercial or applied end of things, both with industry, with government, and a number of other areas. Obviously, I'm not going to cover most of these, but what I will do is use 2 or 3 of these projects to illustrate the concepts that I'm going to cover in the rest of the presentation. And that's really the introduction. What I really want to spend the meat of the presentation on is talking about 3 key concepts that I think are particularly relevant to the robotics research field and how we are going to do research moving forward and assess it and evaluate its worth. And these issues are particularly relevant, I think, for trusted systems for autonomous vehicles and robots that are going to work in off-road or challenging environments, and environments where there is sharing of the environment between people, both in terms of keeping those people safe, but in terms of also facilitating and enhancing the collaborative abilities of human-machine teams. So that's really what I want to cover in the rest of this talk. So the 3 key issues I'm going to cover, all illustrated through industry projects. These are not hypotheticals. These are topics that came up directly as a result of experience working on applied research projects with industry and government. The first one is that all errors are not equal. The second one is a bit of a mild rant on the disconnect between the conventional metrics by which our papers are primarily assessed and the actual their predictive ability for the actual eventual utility of a system, for example, an autonomous vehicle localization system that we're developing. And the critical importance, and this is perhaps the most important point, of introspective capability for all of the systems that we're deploying on systems like autonomous vehicles. And I would argue that this capability, if you had to pick one, is actually more important than the percentage of precision or recall or accuracy that you're achieving in a system, even though those are currently the primary focus of the research field. So as I said, I'm going to illustrate these with actual project examples. And the first project example is a really fun project we did in developing improved positioning and navigation systems for underground autonomous load haul dump trucks. So this was a collaboration between Caterpillar, Queensland Government, Mining3, and a number of other organizations, as well as QUT, our university. And what we were doing is trying to develop improved 2 tiers of positioning system for these load haul dump trucks. These are articulated trucks that are the main workforce underground in a lot of these mines that move material around. And aspects of these have already been automated for many years. We were trying to create improved or more cost-effective positioning systems that would further enhance the capabilities of these systems, both from an autonomy perspective and also from an ability to track where your assets are in the mine. So this is an example of a load haul dump truck. This is one of the sensor rigs that we developed with partners that was put on it. These are quite large, sort of 10, 20 plus ton machines, very large scale vehicles, much larger than a typical robotaxi. So this is an example. You're seeing our positioning and mapping system in action. So this is a 5 to 10 kilometer journey up to 600 meters underground. You can see what this sort of environment looks like, long featureless tunnels, both visually and geometrically. So quite a challenging environment to map. And this is one of the two positioning systems we developed. We used both range-based sensors and cameras to develop these two positioning systems. And basically we trialed it in a number of underground environments, and then we're over to hand over to the industry partner who also recruited the lead engineer from our project and continued the work in-house. It's a really great experience doing this in the field. One of the things we learned from this project is that not all errors are created equal. So I think we have a tendency, at least in our fundamental research papers, to not have the level of sophisticated treatment of types of errors that perhaps would be beneficial for really advancing the field. So in this set of images, what we're seeing is an overhead schematic of a tunnel in the mine. So the blue dots are the walls of the tunnel, and the system is moving down the center of the tunnel. And what we've done is we've split up the components of the positional error from the overall Euclidean area, which is just the distance between where the robot thinks it is, for example, in the ground plane, to where it actually is. And we split this up into the downtrack error, which is the error in where the robot or the vehicle thinks it is along the tunnel, and the cross-track or lateral error, which is the error sideways in the position estimate of the vehicle. And these errors do not have equal significance, and they do not have equal significance at different times during the platform's operational journey. So for a lot of the time, when the system is going down a long tunnel, the downtrack error is not super significant. Whether it's off by a meter or two is not actually critical because it's not making any navigational decisions. The cross-track area, the lateral or sideways error, is often very significant because these tunnels are not particularly wide. These vehicles are quite large, and if you are off by even a meter or two, you might ram your truck into the walls of the tunnel. That might damage the truck, it might shut down the truck, and worse, it might shut down operations in that part of the mine. And even worse, you may need to send in people, vulnerable people, into a relatively hazardous environment to help resolve the situation. So these errors have very different significances. The downtrack error becomes very significant when you are at a T-junction or a fork or a turnoff, because then you do need to know fairly precisely where you are up and down the tunnel. So these errors both have different meanings or significances, and that meaning or significance changes depending on where you are in the operational task that you're performing. You can also imagine that this significance would vary a lot depending on whether you have people in the vicinity of the autonomous truck, and also the exact operating circumstances. So the significance of errors varies all of the time, and I don't think we take enough account of this. Related to this, of course, which is an interesting synergy, is that not all sensors have equal errors. So if you are doing localization with a laser or LiDAR and a camera, against this is an overhead view of the position estimate distribution. The LiDAR or range sensor is very good at lateral localization because you can directly detect how far away your tunnel wall on the left and right is. Whereas the camera is not so good at that, but may be able to localize you better longitudinally. So these different types of errors are unequally addressed or solved by different types of sensors. So this is a really interesting field that I think we're only just scratching the surface of. The second point I want to make, and this is especially important for operationally critical or safety critical robots and autonomous vehicles operating around people, is that we really do need better metrics. And I'm sure that behind the scenes in a lot of the large scale commercial operations that robotaxis are running, they do have a lot of these metrics, but I don't think they have made it sufficiently into the research community. And so that's what I want to talk about for now. So again, this was these insights were born out of a real industry project. This is a collaboration with Ford Motor Corporation, again, creating improved positioning capabilities in the context of autonomous vehicles. This is one of the Ford test vehicles. And the concept here arose directly out of challenges that we encountered during that work. So if you've published a localization paper in robotics or autonomous vehicles, and this is from, I think, a CVPR 2021 paper that we published, these are the sort of tables that you need. You need the bold numbers on a very limited set of metrics, like recall at 1, recall at 5, recall at 10, and then also percentages of achieving certain tolerances in angular and positional accuracy. These are sort of the dominant metrics. And these metrics are very good, but they are not enough by themselves, especially if you want to eventually deploy the system. So what happened was we were working on this project and we were coming up with all these really great innovations to improve localization performance of an autonomous vehicle. And we were also interested in potentially publishing this. And so we'd made all these improvements. They clearly made a huge difference in improving localization in problematic parts of the data set. So we were improving the worst case performance in a lot of areas quite substantially. But we basically made no dent in the global average statistics reported using these standardized metrics. And so that's when I guess we started to really realize that the metrics that we publish and present in papers only really tell part of the story. If you have a system that's operationally critical, often you don't care so much about the peak performance. What you care about is the worst case performance. And you also care about the worst case coverage gaps in localization. And to illustrate that, first of all, there's a graph on the left. This shows the recall at 0.25 meter precision across 40-something 1 kilometer segments of road for this autonomous vehicle data set. And the red bars or columns are areas where the system performed particularly poorly. And we were able to improve these quite a bit. We may have slightly decreased some of the peak performance in other areas. And basically, we were making a system much more functionally useful, but the overall global metrics that we were reporting on weren't really changing. And that was an issue. To illustrate this in a scenario, here are two localization systems on a nominal autonomous vehicle that both have the same global performance. So when you see a blue line, the system is localized within the required tolerance for the autonomous vehicle to operate safely. And when it's red, it's not localized within this tolerance. So you can see it here. This is scenario number 1. And this has the same performance overall as scenario number 2. So you have long, well-localized stretches and long, poorly localized stretches. This is scenario number 2 that we're going to watch now. Shorter segments, more breaks, but the overall performance in terms of the distribution, in terms of the percentages, is about the same. Now, we would argue that whilst these are not perfect hypotheticals, this second case is generally a more desirable case for 2 primary reasons. The first is the vehicle has shorter gaps in coverage. It has more regular gaps in coverage, but they're shorter. And we know as roboticists that you can compensate for short gaps in localization coverage in all sorts of ways. The other reason that the second scenario is arguably better is that the gaps in coverage occur not in the immediate lead up to a safety critical or particularly safety critical area of the data set. So it's not occurring right before entering a pedestrian crossing. And in terms of collaboration or interacting with people, this is also an important factor. Again, we're not arguing that the second case in absolute terms is always better, but what we are saying is that the current metrics we use to assess research do not sufficiently capture these important nuances and subtleties in how our systems perform. The final one is introspection. And again, this is illustrated in the context of projects we've done in a number of sectors, which is all about knowing when you don't know. So again, I'm going to pose this as a scenario where you have to pick between 2 positioning systems. System 1 is a system that works 99.9% of the time, but lacks any self-diagnosis capability. System 2 only works 99% of the time, but in that remaining 1% of the time, 99% of that time, it realizes or self-diagnoses that it's not working well. So it has an introspective capability that the first system doesn't have. So we would argue, again, that system 2, even though for a research paper it may not look as impressive because it's only 99%, not 99.9%, we would argue that system 2 is much more useful. If you use system 1 in a safety critical application, especially operating around people, you'll make decisions based on incorrect positional information unknowingly 0.1% of the time. roughly. The numbers are slightly different to this. Using system 2, this drops by roughly an order of magnitude to only operating off incorrect information unknowingly 0.01% of the time. System 2 is very hard to create. We've been doing a large body of research across multiple projects to develop systems that enable introspection for localization, and many others in the field have been doing this as well. And we think that this is another huge area of need and opportunity in the field. And it relates to a bunch of things around positioning integrity, characterizability, trust. Also indirectly relates to things like guaranteed performance bounds, all things that are important for systems you actually want to deploy in the real world. And so this is a system that Helen kicked off. She's done a bunch of research. She's just finishing her PhD, where you feed in the proposed positioning estimate into one of the introspection systems we've developed, does a bunch of analysis on it, and then decides whether the position estimate the system is proposing should be verified as likely being correct, or whether it should be discarded as probably not being a correct estimate. So this is an additional processing layer, additional introspection layer that you apply on top of your core positioning or localization system. And you can see the system operating here and verifying or discarding positional estimates. And this is really significant for lots of reasons. So in autonomy, you can have a safe, reliable fail-safe. You can hand over to a collaborator or a human supervisor. And if you're doing mapping or learning, you can trigger an update to your existing maps, or perhaps trigger an update that says your maps are completely useless because we know performance is really bad, and you have to remap the entire system. And these are things that are very important from anything as mundane as a robot vacuum cleaner when its map becomes stale and out of date and realizing that it's no longer performing very well rather than relying on a human, all the way to safety critical operations like autonomous vehicles with remote intervention. And this is not autonomous vehicles off-road, but I would just say that this concept is universal. So another example here is this is work led by Morgan, is introspection for surgical robot navigation systems. And one of the key concepts here is when we're talking about collaboration between robots and people, it is not always possible for the person that the robot is collaborating with to observe and understand when the robot is not performing to spec, especially in areas like this, where it might be off by just a millimeter or so, and that is not immediately obvious at all times to an observing surgeon, for example. And they also cognitively are distracted with other things as well. Like they can't be entirely responsible for supervising the robot. They're looking at other parts of the surgical process too. So introspection in this environment is also really, really important, not just for full autonomy, but more importantly, I guess, for collaborative autonomy and collaboration between robots and surgeons in this case. Finally, and this is a topic that I think is only just starting to be looked at a little bit more in the research community, when you are around and operating around people, people can be collaborating with your your robots and autonomous vehicles. People can just be, I guess, passive bystanders in the case of pedestrians or cyclists, where you have to do everything you can do to make sure the system is safe. But people can also be actively interfering with your system in the case of adversarial interference. So people might spoof or jam the positioning signals or localization systems for your autonomous vehicle. And we've seen examples, not necessarily in localization, of people showing that you can disrupt these systems with targeted visual attacks, for example. So one of the other aspects that brings together a lot of these concepts, especially introspection, is baking in the ability of these systems to understand and detect when someone is perhaps interfering or screwing with them, and then taking action or doing more probing in order to establish whether that is indeed true or whether it's just the environmental conditions are challenging, and then taking proactive action to ensure that navigation can still be maintained, perhaps by changing navigation systems, changing navigational behavior, or other active responses to such interference. And so this is an area that we've been working in a lot, including a Cadra RAS Center project, which recently concluded. Once again, a bunch of publications. It's being presented at IROS this week as well. And using these introspective systems to help detect when you are being interfered with. Once again, a very exciting area. So I guess just to wrap up my talk and leave hopefully a little bit of time for questions. If everything goes right, I will be zooming in to answer a few questions. I guess I would identify that there's still a stark divide between the cutting edge fundamental research that we do that gets published in IROS or ICRA or RSS or CVPR, and enduringly deployable, commercially viable research that's sufficiently safe. Like, they are related, they draw inspiration from each other, but I think they're a little bit too split up. And they're particularly split up in terms of how we assess and evaluate progress and performance of fundamental research and how directly that connects to that research's eventual utility in a deployed system like an autonomous vehicle. The upside of this is I think there's huge greenfield research opportunities, lots of opportunity and space to do it. It's not as saturated as other areas. It is a very challenging area to work in. This has been one of the most intellectually challenging areas for our teams to work in over the last few years, but it's also been really, really rewarding and exciting. And I think workshops like today and an increasing number of workshops at conferences are really starting to look at issues like these, which is really, really exciting and a positive sign. So I haven't really done too much deep technical dives on any of our research. Obviously, there's a lot of great people and researchers behind all of this, but if you want to look up anything else or get in touch, please do. We have a lot of resources online and so forth. You can find out more information. Thank you to all of our supporters, our collaborators. Big thank you to our research group and as well as our QT Center for Robotics and all our collaborators around the world. And once again, a warm thank you to you for attending my presentation, to the workshop organizers for organizing such a fantastic workshop and inviting me to speak. And I look forward to your questions and some more discussion offline as well. Thank you very much.